Everyone, it's Mr. Edie back with yet another video. So today, guys, we're going to talk about Unit 5, which is kinetics, okay? And our first topic is talking about reaction rate. So before we get into anything, I want to talk about what kinetics is in chemistry, and it's the study of how the molecular world, atoms, molecules, etc., changes with respect to time. Now, as we've talked about, between your first year chemistry class and obviously AP chemistry, we've really investigated reactions and the various different types of reactions, how we can quantify them, how we can evaluate for qualitative evidence, and so on and so forth. Well, we've really neglected to talk about how chemistry can change with respect to time. So that is exactly where this unit brings us to. And moreover, guys, why is it important to study a chemical reaction with respect to time? So I'm going to use the example of rocket fuel, and specifically being able to launch rockets into outer space. Now, here's the deal with rockets, right? If that chemical reaction occurs too quickly, right? That rapid explosion of the fuel, that combustion reaction occurs too quick, then we could look for the rocket to explode, right? It's too much energy was released all at once, the rocket has exploded. Meanwhile, if we allowed the reaction to occur too slowly, okay, there would be not enough, let's say, energy to propel the rocket to achieve the escape velocity in order for the rocket to go to outer space. So we have to get the timing just right for that specific chemical reaction. And how do chemists do this? Well, we look at the kinetics. We look at how how a chemical reaction is changing with respect to its time. Now, reaction rates are measured as the change in time in the amounts of reactants on products divided by the change in time. You've seen rates before in the form of, let's say, speed in physics, right? So speed in physics is your change in distance divided by your change in time. Well, in chemistry, we're going to look at these rates in a very similar form, but obviously in the form of a chemical reaction. So if I'm looking at my first reaction right here, okay, it's the change in my hydrogen concentration divided by the change in time. You'll notice that there's a negative sign in front of these numbers here, is because hydrogen is a reactant and reactants get used up, right? So therefore, if it's getting used up, we put a negative there, okay? Now, same would be true for the change in concentration of my iodine, okay? It would also be a negative number because it's a I'm sorry, it would also be negative because we are using up the concentration of iodine. Now, the overall rate, guys, the overall rate of anything, this is the average rate of the reaction here. This number is going to be overall positive because rates have to be positive. That's why we're putting out this negative sign out in the first place, because when I calculate my change in concentration of my reactants, that number is going to be negative. And of course, a negative number times a negative number would be overall positive. Okay. Products, however, we're going to have a positive number here. Okay. Because products are being reduced in the chemical reaction. Now, guys, you'll notice that there is a 1/2 in front of here. And so what I did is I took the reciprocal of the stoichiometry coefficient and I placed it in front of my fraction here, my change in concentration of HI over change in concentration of time, because my HI is being produced at twice the rate of how the reactants are being used up. And in order to account for that, we just multiply by 1 over the reciprocal. Now, why is this, guys? Because in order to find the rate of this reaction, okay, the rate of the reaction should be the same for all three of these expressions, okay? And like I said, well, in order to account for the fact that HI is being produced at twice the rate that H and I2 are being used up, well, we put it 1/2 in front of there, okay? Now, In terms of reaction rates, we report the overall reaction rate as positive numbers, as I stated before. So the change in rate of concentration of reactant is negative because the reactants are being used up. And the change in concentration of a product is positive because the products are being produced. Now, folks, you'll notice on this graph here, okay, and I definitely recommend you copy this graph into your notes. This graph, you'll see that, okay, at the very beginning of this chemical reaction, reactant A has pretty high concentration, right? It's roughly 1.7, okay? And as this chemical reaction occurs, reactant A is getting used up. It almost goes down to zero in its concentration. As the rate of reaction B being produced, it starts to increase. Okay, pretty simple there. That makes sense. As a chemical reaction unfolds, reactant is going to be used up. Meanwhile, the product is going to be produced. We expect that to happen, right? I'll note a couple things. At the beginning of this particular chemical reaction, guys, you'll notice that the rate is pretty quick, right? The reaction starts pretty quick with the reactant being used up quickly and the product being produced quickly. But as we approach 400, 500 seconds, the rate slows down quite a bit. Okay, now there is a reason for that. We'll talk about that reason in the next video. But in terms, this reaction has a starts fast, and it ends slower. Okay, so keep that in mind because we're going to have to account for that in just a slide. Okay, so average versus instantaneous reaction rate. So let's consider the reaction AA plus BB yield CC plus DD, where capital A and capital B are the reactants, capital C and capital D are the products, and lowercase a, B, C, and D are the stoichiometry coefficients. You'll notice that the way we calculate the average rate of this reaction is to take negative 1 over the stoichiometry coefficient times the substance over the change in time, right? I'm sorry, times the change in concentration of the reactant divided by the change in time. For reactants, we have to put a negative side out front. For products, we keep it positive, okay? And this average rate of reaction, guys, would be the same for any of these values, okay? Now, guys, there's one thing that we have to understand. Just because I can write the expression using a balanced chemical equation, I need more information to actually calculate the rate, right? I need the rate of change. I need the rate of change, for example, of a product being produced, the rate of change of a reactant being produced, or I could be given that graph very similar to the previous slide, but I need information with change in concentration of something, which with respect to change in time, in order for me to actually calculate the rate. The best I can do with a chemical reaction or a chemical equation, guys, is just write the expression. Now, that's how you get the average rate. So again, it's 1 over the reciprocal times the change in concentration of that particular substance over the change in time. If it's a reactant, we add a negative sign out front. If it's a product, we keep it positive. Now, as I just got done saying on the previous slide, because the rate can change over time of a chemical reaction, we have to be prepared to calculate the instantaneous rate at any given point, okay, which is represented by the instantaneous slope. So how do we calculate this? Well, we would determine the slope using the slope of the line tangent to the point of interest. So for those of you who are pre-calc or calculus, this would be obviously the derivative, okay? Now, guys, I'm not going to get into the calculus. Like, you don't have to worry about doing the calculus. I'm going to show you how you would find it for me in the event that you would need to in chemistry. We are going to use the line tangent to that number, okay, where we'll be able to calculate the instantaneous rate, for example, of reactant A at 200 seconds here. But keep in mind, it's not like I'm not going to expect you to know like you're not going to do calculus in here. I'm just showing you that the reason why you learn calculus is so you can use it here in chemistry. So for those of you who may be in pre-calc and not actual calculus, this is a tangent line, this blue line right here to this point, okay? And the way that you would find the slope of this is, of course, you would find rise over run. So here's your rise, and here's your run. And then after you take those two numbers, you divide by them, you get the rate of this particular line. Now you'll notice that it's right here, right? So that's my rise divided by my run, and I get my slope, okay? So when we're talking about this line here, we're asking to find the slope or the instantaneous rate at reactant A at 200 seconds. Okay, so it's going to probably be right around here. Okay, now forgive my line for not being perfectly straight. And guys, you'll notice I'm just going to make it easy on myself, and I'm going to draw my line to the other 2 points for my point of interest. Again, my point of interest is 200 seconds, so I will outline that more in purple. And then I'm going to do my rise with my run. So I'm going to bring my run down to about here. Okay, and then I'm going to bring my this is my rise, excuse me, and then I'm going to bring my run to the other point. So I draw that triangle. Okay, and let's just come up with the equation that essentially we're going to be using to plug this in. So here we go. So my instantaneous rate, okay, is equal to the slope of the tangent line. Okay. We know from algebra class that slope is simply rise over run, right? And further, since it's rise over run, folks, we also know that my rise is obviously my y-axis, so that's going to be my change in concentration of A, okay, from these 2 points, and then divided by my change in time, which is my run. And how do I know that's my run? Well, the x-axis is time, right? So when I go to plug this in, my instantaneous rate is going to equal, okay, so we're starting at 0.2 molar and we're going up to 0.6, right? So 0.6 minus 0.2, okay, that's my rise, divided by my run, which is going to be roughly 250 seconds minus 150 seconds. Okay. All right. And when I enter this in my calculator, I get 4.40 times 10 to the third, capital M for my molarity, molar. And then the bottom is obviously with respect to time, so seconds. So my instantaneous rate at 200 seconds is 4.40 molar times 10 to the 30 molars per second. And I will put that there. Okay, so that's how we would find the instantaneous rate if you needed to find it. Again, folks, as I said before, this is something that you don't like. We're not going to particularly do this and a lot of problems. It's just so you can see the connection between calculus and, of course, chemistry. Okay, let's continue on. So we want to start expressing the reaction rates. Okay, so let's consider this chemical reaction. H2O2 plus 3I minus plus 2H plus yields I3 with a negative charge plus 2 molecules of water. And it says in the first 10 seconds of the reaction, the concentration of I minus drops from 1 molar to 0.86 molar. And the problem's asking us to, 1, calculate the average rate of this reaction in this time interval, and then 2, determine the rate of change in the concentration of H plus, that is in the form of delta H plus divided by the delta T during the time interval. All right, so let's dive right into this, guys. So my rate, of course, is going to be equal to negative, because we're a reactant, 1 over 3, because I have to take the reciprocal of my stoichiometry coefficient, times the change in concentration of iodide, divided by the change in concentration of time. Okay, so when I do that, it's negative 1/3 times 0.868 minus 1.00 molar, Remember, we do final minus initial here, guys. Don't worry, that negative number is going to be canceled out. Divided by the change in time. Well, they gave us the change in time. It's just simply 10 seconds. Okay, because it started at time 0. So 10 minus 0 is just 10. And we're going to get 4.40 times 10 to the third molar seconds. Okay, that is the average rate of this particular reaction. Okay, so now that we have our average rate of the chemical reaction, I can solve for this. So watch what we're going to do. We're going to say, well, the rate is equal to negative 1 over 2, okay, times the change in concentration of H2 over the change in concentration of T, okay? We are looking for this entire variable that I'm circling, okay? So we're solving for this. Okay, we're looking for this entire variable here. So if I solve for that, the change in concentration of hydrogen with times over delta T is going to equal negative 2 times the rate. So let's plug this in. So it's going to be negative 2 times 4.40 times 10 to the third molar per second. We multiply by 2 the change in concentration of hydrogen over the change in concentration of time would be equal to 8.80. Don't forget the negative here, times 10 to the third molar per second. Now, why am I allowed to have a negative number here, folks? Well, remember, the reactant is being used up here. Okay, so that's why we get that negative 8.80 times 10 to the third molar per second. That's the rate in which, that's the rate in which that the hydrogen is being used up. All right. And with that being said, guys, that's this example problem. Okay, so let's move on to the next one. So the next one says, for the rate of reaction A plus 2B yields C under a given set of conditions, the initial rate is 0.100 molar per second. And I want to know the change in concentration of B with respect to T under these same conditions. So take a moment, guys, and solve this one on your own. Okay, everyone, I hope you were able to get letter C. As you can see, my work is shown for you. Very similar to the number 2 from our previous example problem. So hopefully you were able to get letter C. There's the work that I did. Let's continue on. All right, so how would we measure a reaction rate? We can use something called polarimetry, which is the polarization of light as it passes through a solution reactant. We can also use spectroscopy, which is what we did with the analysis of our red food coloring Gatorade lab a couple months ago. Okay, you can, instead of just simply looking at how concentrated a particular pigment is, you can also look at how fast a new pigment is being produced, and that's how you would use the spectroscopy there. And then finally, you could also use gas chromatography, which is combining chromatography with obviously the production of gases. Okay, so if we were to do anything in the laboratory, guys, we would be using the one with respect to spectroscopy. Okay. Moving on, I want to talk about how we can make chemical reactions happen faster. This is a preview to the collision theory, guys, that we're going to talk about more depth later on in this chapter. But aside to say, with collision theory, guys, in order for a chemical reaction to occur, right, not only do molecules have to collide with each other, but they also have to have the correct orientation with sufficient energy. Okay, so what I would copy down for today, guys, is the major ideas on this and the the peach colored boxes that explain everything in depth, you can leave them out for now. Like I said, we're going to cover this again in more detail. So according to collision theory, if I have sufficient energy and if the molecules hit at the correct orientation, I will have a chemical reaction. So how do I increase this? Well, I can increase the concentration of the reactants. By increasing the concentration of reactants, the number of collisions will increase. And if the number of collisions increase, it also goes that the number of successful collisions are going to increase. So increased concentration of the reactants will make a reaction happen faster. Now, I could also increase the temperature of the reaction. So if I increase the temperature of the reaction, now I have more particles that have simply sufficient energy that are required to react in order for the reactant to go. So you can see that in that Maltzman, the Maxwell-Boltzmann distribution in the upper right of this graphic. You'll see now by increasing the temperature at T2, there are more particles that have the sufficient energy to react, so therefore the reaction unfolds. I could also increase the surface area of the reactants. By increasing the surface area of the reactants, the number of collisions will increase, and if the number of collisions increase, well, guess what? The number of successful collisions will increase. Finally, I can increase the pressure of the reaction. By increasing the pressure, I actually decrease the volume. And by decreasing the volume, the particles are forced to interact more, therefore increasing the rate of reaction. And like we talked about in thermal chemistry, if I use a catalyst, guys, I can lower the energy of reaction, which will then thus increase the rate of reaction. And for guys, we're going to leave it here with this slide. Okay. If you have any questions, please feel free to let me know.